This demo shows how Resonate has been applied to unmanned underwater vehicle, in this case the bluerov 2, which is a small submersible like you see here. So this vehicle is tasked with following a pipeline on the seafloor, which you see as the blue line here, but it also has to avoid obstacles that may appear while it's doing this. So here you can see a small obstacle has appeared in our path, so we're performing an avoidance maneuver to go around it. We'll see a second obstacle appear here in a moment. The bluerov has some other functions it can execute, such as waypoint following, return to home, loiter, emergency surface. And some of the hazards we're concerned with in this system is the potential hazard of an obstacle collision, the chance of losing the pipeline, and possibly exiting the defined operating area. So here in this video, you see it was able to avoid both of those obstacles. So for the Resonate application, we're interested in how bluerov 2 or UV is able to operate under degraded conditions. So you might be able to see a few thrusters here. The bluerov is a thrust vectoring controlled vehicle, so it does not have any fins. You simply turn by vectoring your thrust. There's a total of 6 thrusters, and when we introduce degradations, we'll degrade one or more of these thrusters and see how the vehicle is able to keep performing pipe tracking and obstacle avoidance with this degraded state. So these obstacles can be static obstacles of varying size. They can also be dynamic obstacles like shipping traffic, which may broadcast their current position and heading and so on AIS service or similar. There's a few contingency plans we have for this system, but the one we'll be looking at is thruster reallocation. So that is essentially remapping the thruster control law when certain errors occur. Because, like I mentioned, this is a thrust vector controlled vehicle. If one or more of the thrusters is degraded and you perform thrust vectoring the same way as you would under nominal conditions, then the vehicle will not behave like you expect it to. So we can try to identify which thruster is degraded and revise our control law to take that into account. And that's what we call thruster reallocation. So this shows a relatively full-sized bow tie diagram for this system that we've constructed. This shows how there's different classes of threats, everything from static obstacles, dynamic obstacles, as well as AIS objects, which are dynamic and they're telling us where they're going. And we have a number of different barriers in this. However, we're going to look at a slightly simplified version where we start with a simplified threat. So the threat in this case is just the obstacle far encounter. So we encounter some sort of obstacle at a distance less than the desired separation distance, which in this case, I believe, was 30 meters. So the bow tie diagram I constructed here shows the hazard for the UV operating in the presence of obstacles. And because of that, if we encounter an obstacle, we will try to perform an avoidance maneuver and avoid that obstacle. Use a forward-looking sonar to detect the obstacle and then execute an appropriate avoidance maneuver. If that fails, we may have a top event occur. This is where we get a little too close to the obstacle. And so this is where we break our minimum separation distance requirement. So this was set at 5 meters in our case. And if that happens, we can try to stop the vehicle entirely. This is, there's no brakes on a UV like there might be on a car. However, you can reverse your thrust and try to stop by thrusting backwards, essentially. If this also fails, then we may collide with the obstacle. So in this case, we estimated the probability of barrier B1, or the avoidance maneuver barrier, and got these functions here. So these are two sigmoid functions which show the relationship between S.dd is degradation detector, and this detects the level of thruster degradation that's been injected into the system. So these two functions show the levels, the relationship when no reallocation has been performed and then after thruster reallocation. And from the equations, it's not easy to see what these sigmoid functions would look like, but they've been plotted over here on the right. So you can see the probability of barrier failure. So we want this number to be low, and it's plotted against the level of thruster degradation, anything from 0% degradation to 60% degradation. So the blue line shows the no reallocation case. So this is the behavior, the conditional behavior before we do any reallocation. So you can see if we have no thruster degradation, we have a relatively low probability of barrier failure. And as the thruster degradation level increases, we get significantly higher chances of this barrier failing to perform like we expect it to. If we perform reallocation, thruster reallocation, then you see we get this dashed orange line. And this line is slightly higher than the best case scenario in terms of the probability of barrier failure at about 40%. But you'll notice it's relatively flat. It's almost entirely flat. It is still a sigmoid, but over this short interval from 0 to 0.6, it appears flat. So that indicates that even as the thruster degradation level goes up, as long as we reallocate and adjust for it, we can keep our probability of barrier failure relatively constant. And these numbers, I should mention, these equations were fit from a total of 350 simulation runs, each run consisting of approximately 1 to 3 minutes. So this example video will show how the bluerov, while following a pipe and using resonate, we get the hazard rate, or the lambda parameter here in this top plot. The next plot shows the level of thruster degradation. And then the bottom plot shows the level of thruster reallocation performed. So you'll see we encounter an obstacle here. The UV performs an obstacle avoidance. And then we introduce a 60% thruster degradation. So because our thruster is degraded, we see the risk score increase, the hazard rate jumps up. But then we perform a thruster reallocation to adjust for that 60% degradation. And you'll see our risk score comes back down to slightly above the nominal case, but still significantly lower than it was when the thruster was not adjusted. So now we encounter another obstacle. And since we've adjusted our thruster, we're able to control the vehicle like we intend to, perform the avoidance maneuver, and then return to our task following pipeline.